So we're here to solve this Sunday Stumper by Serkan Yürekli. It's a TomTom Cipher puzzle. One of the things we'll do right at the start is just make our own notes on the right side of the grid for all the letters in Father's Day that are going to have to be turned into distinct digits. There's a lot to kind of parse in this grid. One of the things is we've got a specific cage, which is an S division, which is going to have to be a very small number. I'm going to think in my head if I can make that be a 3 or any digit larger than a 3, but 3 is really like a small multiple. That would mean that I would have something like a 9 coming down from a 1, 3 with another 1, but I'd have to put in a second multiple into this. If a 6 were coming in, I could be taking out a 1 and a 2, but again, I'd have too much coming out of this. And the main way to think about this is we're going to have as many as, in the largest value, something that has 3 multiples to it, and that would actually be the digit 8. And if I had 8 in there, I could have 2 2's taken out, leaving behind a 2 for this value. But in most situations, I'm going to have all the multiples taken out of the large value, which comes down to a 1. And notice that even when I have this value of 2, I'm always getting 2 1s into this big cage. I think that's another important deduction in this part, is that we're going to have a 1 in this row and another 1 in this row, so that we can get a valid 1 divide or a 2 divide out of this. A different thing we can do is we were told in the instructions that a 2-digit number never starts with a 0, so we know that y is greater than 1. Sorry, greater than 0, it's 1 or greater. F is 1 or greater, D is 1 or greater, T is 1 or greater, E is 1 or greater. And I've got then 3 values that could potentially be 0 or anything else, but I've got 6 that can't be 0. This YR looks interesting. It's probably not able to be a product. Actually, 1, 2, 3, 4, 5, 120 is the smallest product you could have here, so that's not going to work. So this is always a sum. And as a sum, where this could be in the single digits, like a 1, like a 15 or 16, out to 19, if I put all the digits from like 1 through 5 in here, even some of the small digits like 1 and 2 in here, I probably can't make this S work. This S really looks to be a division or a subtraction. 6, 1, 2, 3 would, for instance, work with at least 4, 5, 7, 8, 9. And that gets me all the way up to 30-something. So Y really wants to be a 2 or a 3, but for sure it's no larger than a 3. And as I'm looking through the grid, I'm seeing another case. This YY in the lower right is going to have to be a sum. 11, 22, 33, those would need a multiple of 11, which we can't put in this grid. So if this being a for sum, 987 with a 9 would let 33 work, so all these values are still okay. But we've got another constrained digit that's probably 2 or 3, but at least for now I'll just mark as 1, 2, or 3. The next thing I am being drawn to, I guess, two interesting facts. First, F and D are partners, so one is a first digit becoming last digit becoming first digit, so that's going to have some interesting constraints. But also I've got two cell cages that start with D, DFDA, and also FDFR. And I think that's going to force a constraint on the size of D or F. One thing for sure is it can't have like an 8 in the start of a 2-cell cage, because 81, 9 times 9, the only product I can see in that space, would never actually work in the puzzle at all. So if you had one 2-cell cage in a row, you could be as large as 7. 72, 9 times 8 would be okay. But when you're doubling things, we have to come all the way down, I think, to what will it be? 6 would be only 63. 5 would be 54 and 56. That 54 would be 9 times 6, and 56 would be 7 times 8. You could get a 54 and a 56 to be valid spaces for this. So D and F can only be as large as 5 because of the fact we have two cell cages that start with D's and F's. And so they could be sums starting with 1, or they could be products, but they can't be a product that's larger than a first digit of 5 in that 2-digit number. Let's now come back to what we said. FD and DF being partners is pretty interesting. If D, for instance, is a 3, or if F is a 3, we're going to need to have the last digit of a sum or product being that 13 looks okay up here, but 31 is never good. 32 is okay down here, but 23 is not. 34 and 43 are bad in both places, and 35 is okay, but 53 is bad. And so 3 is a bad digit to be both starting and ending. And where we talked about 4 and 5 being limiting, maybe we should put in one of those to test those out. Let's take the largest example of 5 as a first digit. 51 and 52 can't be a product. 17 and 13 are prime, but not able to come in there. If this is 54 and 45, I have 9 times 5, and I have 9 times 6. And I need 2 9s to fill in this column. So the 5 looks to be dead for D and F, and that means I now have gotten D and F into the space of 1, 2, 4. I know that S is 1 or 2, so those are forming a triple, and that leaves just the digit 3 for Y, and everything else now has to be 0 or 5 or larger. So this E and T I can mark now as 5 plus. Knowing that this is 33, we had 9, 8, 7, adding up here to be 24 plus 9 to be 33, so we'll mark that in. I'm crossing off the clues when I really fill them in so I don't have to look at the numbers and be confused by them, but in this case where I don't yet know what the thing is doing, I'm going to put in that 3. 3 in this SY cage, this could be 13, but it can't be 23. 23 isn't a valid sum or product. So S is always 1, which means DF is going to be 2 and 4. That means this is 1. This is also now 1 divides. This is 13. This is 2 or 4. And maybe R as a digit I want to think about is also over here. It's also right here. R is a sum of 5 digits that starts with 3. 98765 is as large as that can be, which is 35. So R can be 5. And it can be smaller than 1, 2, 3, 4. It can be 0 as well. But it can't be 6, 7, 8, 9. I can't get up to that space with a sum, and this operation has to be a sum as we talked about before. So this R is 0 or 5, which means I'm going to have the 5 somewhere in this cage, and a few things that means. I think I can actually look at this point and see that 25 is no good, and actually 45 is no good, so I could say that this is a 0. But another way to kind of work through this is this 13 cage has to be a plus. And this plus when 5 and 9 are in the row means the only options left for it are 6 plus 7. That means this is coming over here as an 8. 4 would need to be 8 times 5 or 9 times 5, so F is now always 2. And in making that 2, we get, again, to the set of deductions we were seeing that R is 0, F is 2, and D is now left over to be a 4. So a lot of work to get here, but some pretty fun deductions along the way. A lot of good interplay of the cages. This DF, FD set is actually pretty brilliant when I think about it. So 42 is 6 times 7. 24 left over is not 4 times 6 now, but can be 3 times 8. This is 20. We don't know if it's a product or sum. This is 4 something. Still an A. This is 1 something, still an A, so probably A is the next letter to focus on. But before we jump too far away, we did a lot down here. Let's see if we can make some more headway. H can't be any smaller than 5. And in this row, I've got 1, 2, and 3 to go. And if 1 and 2 are over here, I'm never going to get large enough. So 3 must be in the cell. But even if 1 is in the cell, 3 and 1 could get as large as 4, but 4 is already taken. This has to be 3 and 2. And H is 5 or 6. I get a 1 in this lower left cell. We marked that this Y plus is 30, and that means that the sum of the digits down here in this one cage will be 15. If 9 were in the cell, there's no division that makes it work, so it's to be 9 minus the sum of 8 would be 17, so 9 is not down in the bottom. It's got to be in the 30 plus. If I skip over the digit 8 and come down to 7 being the largest digit here, I'd have 4 and 2 left over. That comes to 13, again too small. 6 would have 1, 2, 3 as a division, again too small. So this does look like it's an 8 with 2, 4 being forced, so I have a sum of 15 below. This is the only division that's 1 that gets me or subtraction. This is actually division or subtraction, but this is the only split of these digits from these digits. It gets me to 15, and I have 3, 5, 6, 7, 9 up top. Just marking in these somewhat exhaustively. We can still now come back to this A situation. So A is a digit that's 5 or larger, and it's got to be a product that can start at 4. So 45 with 9 and 5 seems possible, and 46 does not, 47 does not, 48 with 6 and 8 seems possible, and 49 is again not. So we've got two options for this, 5 or 8. This would be 24, and this, if this is 18, would take me to 42, so I would have a total sum of 3 in one option for up here for the R, and this R is going to be 0 minus, where we know R is a 0. So that means I could have a 1 or a 3 in the cell. And if A is 5, I've got 15 down here. 15 and 24 leaves behind 6. So this could be 1 and 5 or 2 and 4. In those situations, 6 is a thing I could subtract from both of those, or I could have a 4 in this cage, which would be okay to subtract from these, or I could have a 2 with the 2, 4. So a lot of small options in this cage. But I think a thing to see is that we mostly have small options coming over here. Let's now come back across to this 20, and we could say, is this a product or a sum? If it's a product, I'm going to get 1, 4, 5 in the space, which is then also going to make, it looks like this will always have to be a 2. I'm going to have a 3 or 6 in the space, so all these small numbers. Where am I going to get like 7 and 9 to come in? So I think 7 and 9 are key digits here, which if this is a product, I can't put into the space. And if this is a product 1, 4, 5, then this A can't be 45 because another 5 would want to be here. So this is an 8. This would be 68. So if this is a product, then not only is A forced to be 8, but I have only this cell to put a 7 in, as well as only this cell to put a 9 in. So that doesn't look good at all. This is a very big sum. And now that I see it's a very big sum, I can eliminate the digit 1 from this area. A 1 can't be over here, a 1's not here, and a 1's not going to be in this product, whatever it is. So there's always a 1 here. And doing the same thing now actually with the digit 2. 2 can't be here, 2 can't be in a 20 plus sum, 2 isn't in this product, 2 is not in a 45 or 48, so I have 1 and 2 in these first two cells. The only option that works for this last cell, it can't be the 3 because we didn't have any division of the grid that had a 3 in this space, so this has to be 1, 1, 2, and that actually now implies that A is equal to 8 for sure. This is another hard deduction, but one that you can think through a few different ways, but once you find it, the whole grid starts to click into place a bit. So 3, 4, 5, 6 come up here for a sum of 18. This is 48 with a 6 times 8 coming across. That puts an 8 down here and a 3 up above. I've got 4, 5, 7, 9 left over, and the 9, 7 always are in this cage with the 4 to get to 20. And that puts a 5 into the upper right cell. This 3, 8 actually eliminates one of the options down here, so you can put in 3, 2. We still don't know if that's a 5, 6 or not. This one puts a 1 right here, which now puts a 1 over here. And let's track some of the remaining values we know. We have a 48, which will be a sure product. F and A, we've got a 28, which could be a product or a sum. F down here is a 2, probably a subtraction, could be division. This is 15 or 16. That still looks like it's got some options. This is 8. This is 42, so this is 6 times 7. Actually marking that in now is going to limit this. So this 8 can't come down here because it would be 8 with 1. So this could be 2 with 4 as a product, or 3 with 5. This being 15 or 16 has a lot of choices, 2, 8, 8, 2, 8, 7, or 3, 5 if it's 15. So I don't see much down there. This TH could be interesting, so it's going to end in a 5 or 6, and it's got to start. Now if the 8 actually given, we have in principle t being 5, 6, 7, 9. If t is 5, this is 56. That would be 7, like a 7 here, times 2 times 4. That would be okay. It couldn't be 7 times 1, 8, because we've got 2 1s there, but I can make 56 make sense. If it's 6, that would force it to be 65. 65 isn't going to be possible. Prime factor of 13 in there is no good. This is 7. This is 75. And 5, 3, 5 would be okay for that product. Still like a 2, 4 up here. Could have like an 8, 7 down here. It looks like nothing is quickly canceling with the 75. And if this is a 9, 95 is no good because it would have a factor of 19, but 96 would be okay. So I have these 3 options, and I didn't actually get a lot of headway by working through those, but I guess I have 5, 7, 9. I know this is odd wherever it appears. A different cage that we haven't then looked at is this ER. The R is a 0, and this E is again going to be 5, 6, 7, 9. And in marking that in, we should see that this 0 forces a 5 to be somewhere in this cage. And let's just think about the minimum we can do for this space, which is something like 2, 3, 4. That adds up, that multiplies to 24. If a 5 is up here, that's going to get us to 120, which is too large. So the 5 in this cage is always down in this 5th row. And we probably have some constraints on the other digits that go in here. Like I could, for instance, potentially make this be 2, 3, 5 and fill that all in. That's going to have some constraints here and make this be a fairly big number. But let's just think about this. This would be 30. It could have a 2 here, or it could have a 3 here to get to 90, but actually 3, 3, 3, we couldn't have another 3 there. So this could be as large as a 2. And if this is not a 2, but has like 3, 4, 5 in the space up to 60, this can only be a 1. So this cell, which looks like it could be 1 or 2, is a cell we want to probably focus a lot of attention on and eliminate that 2 option if we can. And I'm going to look at that a bit by also focusing on this cell. This cell is not a 5, so right now it looks like it could seem to be a 2, 3, 4, or 8. And that big value is going to force, like an 8 down here is going to force 1, 2, 4 here, which is going to force this. So all the multiples of 2 would be placed, and that looks pretty interesting. So I'm guessing this 48 cage is going to be a key one to look at. So let's start to think about this. This is a sure product, and the multiples that get up to 48 include 2, 3, 4, 6, 8. So these 2 cells on the left can be all those values. Ones already are eliminated from these cages. We've got 2, 4, 6, 8 for this cell, and we have 1, 2, 4, 6, 8 for this bottom cell. So they're saying this again has a lot of multiples of 2. So there's a case where if this is forced to have multiples of 2, this is multiples of 2. What's left over? If this is 8, I've got 1, 2, 4, puts an 8 down here, so I'm left with 3 and 6. 3 times 6 is 2 factors of 3. 48 has 1 factor of 3. 18 is not going to get to a product to get to 48. So if I have all the multiples of 2 in these 4 cells, I've got a problem. And 8 forces all the multiples of 2 in this space. And it's also the case a 4 would force all the multiples of 2. If a 4 is down here, I have to put 1, 2, 8 here, which puts a 4 there. And again, I'm left with 3 and 6. And those are bad digits for those spaces. So this is a 2, 3 in this cell. And this being small, now is going to put a constraint back in the space. We'd gotten to where this could be a 2 if we had no larger than a product of 30 in the space. Let's see if we can do anything different than that. The 30 was from 2, 3, 5, and 2, 3, 5 no longer works, so I've got to come up at least 1 digit. 2, 4, 5 would be a product of 40 here, and 40 could come to 40 or 80, but neither of those are valid for the E, so 2 can't work with 2, 4, 5, and the next largest thing we can get to, either 2, 5, 6, which is 60 is too large, or 3, 4, 5 is 60, 2 would be too large. So now that we know this digit is small, we know this digit must be a 1. Bit of convoluted logic, but hopefully you can follow enough of it to get to this deduction. Where can we now take this progress? We've got a lot of 1s here, so actually this column is now pretty complete. This has 4, 5, or 9 left over. And I think where we had eliminated these things, we were seeing that 4 was potentially an issue up here. 4 is in here, I've got 20, and I could put in a 3 9 with 2 would be okay. I'm not sure I see anything directly there. Maybe it's coming from thinking about how do I get to this 3 value. If I have 4 with 5 without this 9, I actually see no way at all I can get to a 3, so there's always a 9 down here. And then this is a 4 or 5. Whichever that is, that's going to, if this is a 5, it puts a 1 in the cell. If this is a 4, it puts a 2 in the cell. There's already a 1 in this column. So this wants to be a 2. That means that this whole space coming up is 4 with 9. Puts a 5 in here. Do a little bit of cleanup of the digits we've got. This 2 no longer is an option there. This 2 is no longer an option here. Let's actually take another view of this 2, 3 and say, is it possible this cage does not have a 2 or 3 in it as well, whichever digit is not used here? That would require 4 and 6 to be the starting points, and that would take us to 120. So this always has a 2 or 3. And admittedly, if it's in this cell, it's got to be the 2. If it's in this cell, it's got to be a 3 based on the digits we've got there. But 2, 3 are eliminated from cells like this. 2, 3 are eliminated from this cell. This actually puts in a 5. Now I got a 4, 6, 4, 6, 8. That looks sort of interesting. So I'm going to focus down on that pretty soon. And I think I'm going to focus specifically on the 8 here, which would make this over to be a 4, 6 pair if I could do that. If this is an 8, then I have 6 left over for the whole product. That means this has to be a 2, 3. It means that then this has to be a 1. And so let's see why that would cause an issue. And it's probably going to cause an issue because of whatever remaining digits are in this clue. This 2, 3 we said isn't going to be just multiples of 2. So if there's a 2 down here, there's a 6 in this row. And if there's a 3 down here, there could be a 6 or 9 in this row. So we don't know for sure which digit is in here, but this is not 8, 4 with a 2, because that would cause an issue. This has to be a 6 or a 9 to be another value with a multiple of 3 in it. And when that 6 or 9 are down here, this 6 would be a 2 with a 3. So there's a 2, 3 in this space. This 9 would be a 3 with a 3. So I always have a 2 or a 3 in the space, and that means I can't have both a 2 and 3 over here. So coming back to what I was just trying to talk through, an 8 for this value would force a product of 6 for these two cells, 2 of 3, but that now clears everything from the space. So the 8 is not in the cell. We now actually have a 4, 6 pair. That is going to eliminate some options there. We don't have any option where the 8 can go into this big E cage. Again, we had 40 and 80, which are eliminated, so there's only one spot in this row left for an 8, which is right here. That means a 7 or 9 go into this cage. And the 7 or 9, we're getting to a multiple. It ends in 0, so the 2 is the forced digit in that space. So we have 7 or 9 in this cage. We're going to have a product of 70 or 90. That puts a 3 over here. This still is 2, 3, but now it's going to be 6 with 2 or 3 with 9, if that's helpful to see. We have some more constraints we can now think through. Actually, with this 2 being placed, we've eliminated, so these are all big values. If this is an 8, actually if any of these cells are 8s, we now have to put in a 6 in the cell and leave 1s in 2 more cells, and that doesn't work. So I can cancel this 8, this 8, this 8. That now actually gives me a 4, 6, and a 4, 6. Minimum value is 16. 6 times 4, 24. So 16 or 24 are how those multiply. One thing I can't do is have anything but a 1 in this cell. And the remaining digit in this space will be a 2 or a 3. So having those in, I can clear the 2 over here. There's actually no other space for an 8 but this top cell in this whole row. So not an 8, not an 8, not an 8. That now means this is 4 over 2. Because of the digits here, that means this is 4 down below, 9 up top, 9 down below, 7 here. This puts 7 up top, 6 down below. So making a fair bit of headway. This 3 also forces this to be a 3, 5, and makes this be a 5, 8 in some group. We had an option where the 5 would put a 3 in here, or this 8 would put a 2 or a 7. I think now we have to say this is a 3 or 7. And notice if that's true, so if I can no longer put 8 and 2 in the space, I can't get to 16 in any way. And so this h has to be a 5. And so t is 7 and h is 5, and 75 is the value for this cage. And we showed before that's 5 times 5 times 3. That now means where e could be 7 or 9, it has to be 9 to make this whole thing be 90. So this is a 9 here, and this is a 7 over here. What does that do? That means this cage is a 3 or 6, and this is a 2 or 9. These 3's cancel this option down here, so this is a 7 with an 8. T is now equal to 7. So one thing we have is a 1 that comes over here, and actually the last one is in one of those cells. This is a 1. It can't go with a 3, it can't go with a 5, so it's always going to go with a 6. That means this is a 3 and this is a 5. These 6's mean that a 4 goes in the cell because they're clearing up top. Puts a 6 over here. This 3 means that we actually have the last options for this cage being the 6 and the 2 being the multiplication option. We don't have a 3, 9 option anymore. From the canceling, the 6 puts the 6 and 8. We've got 4 and 5. This is 5. This is 4. We've got a 4, 7. In this space, we have 8 and 9 still to go. This is an 8. This is a 9. We have 3, 5 over here. This 4 leaves a product of 12 to go. The 2 is already used, so this has to be a 3. Makes this have to be a 4. This then is a 5. This is a 9. That 9 divided by 3 is 3. That looks fine. Puts a 5 in here. These two 4's put a 4 in this top row here, leaving a 7, 9 for the last cells. In that space, 2, 4, 2, 4, eliminate the 4 over here, so the 4 goes below and 3 goes above. These 3's come over here, and we're left with 6, 9 in this cage. These two 6's and these two 6's, this is the last space for a 6. We have 7, 8, 9 coming up here, so an 8 will be in one of those cells. What do we have? We have some things maybe with the digit 2, where we've got to put a 2 at least in one of these cells. Maybe the cage we haven't looked at all, like this 2, is an important one to think through. Actually, I'm seeing the digit 5 is one I actually want to look at right now. This is the last place for a 5 on the grid. That means that a 1 can't go in this cell. So 1 comes over here. We've got 6, 6, 7. The 7 puts 7 with 9. That means I've got a 9 here. I have 2, 8 to go. I've got to put 2 up top, 8 down here, 8 with 9, 9, 6, 6, 7. Just pushing out. This is a 2. This is 10, 20, 28, so that's a valid sum. This would be 5 and 7. 7 minus 5 is valid. 7, 4, 4, 2. And we finished this Sunday Stumper. So hopefully you had the patience and endurance to go through the whole video with me. It definitely had a few sticking points, so even if you were jumping around to get to the sticking points that hit you the most, key steps at the start were definitely looking at these digits S, Y, D, and F and seeing that they all have to be small, working out eventually their values, working out the value of R, getting to that stage of the grid. Then I think the interactions of this 48 times, this 1 divide, and this something ending in 0, that core of the heart was probably the hardest part of the whole solve, and really dealt with careful tracking of digits, finding, for instance, that an 8 can't go into these cells. It has to come to this one position. That then limits how in this cage we can put other digits through. So obviously a challenging puzzle, really, really great construction though from Serkan, so hope you got something from this video, and we'll see you again soon.